Hello, this is Dr. Hanaa Assil, and this is about reversible reactions. So let us talk about the basics of a reversible reaction. We know that most reactions go to completion. So reactants react to form products and the reaction ends. For example, neutralization reaction, sodium hydroxide, a base plus an acid gives salt plus water and the reaction ends. Or combustion to give carbon dioxide and water and the reaction stops. Displacement, zinc plus an acid, this also is a reaction that goes to completion. Combination reactions in which we have one product formed, all of these are reactions that go to completion. That means they react, they change from reactants to products and the reaction ends. But some reactions are reversible. Reversible means the reaction goes both forward and backward without going to completion. So the reactants react to form products, but then the products break up to form reactants again, and then the reactants react again to form products, and so on. So examples of these reactions, for example, we have the Haber process. The Haber process is the reaction of nitrogen plus hydrogen to give ammonia. We know it is reversible because of this sign. So when the reaction has this sign, that means the reaction is reversible. The contact process also, sulfur dioxide changing to sulfur trioxide, that is an example of a reversible reaction. Another one is the copper sulfate 5-water, which is the hydrated copper sulfate. And we know that hydrated copper sulfate is crystals that have water in it. Now, when we heat it, the water evaporates, leaving the anhydrous salt, which is white. Now, if we want to go back to the blue, what should we do? If we add water to the white, it becomes blue. If we heat the blue, it becomes white. So this is a reversible reaction. Another example is breakup of ammonium chloride to give ammonia plus HCl. So if we heat the ammonium chloride, it changes into ammonia plus HCl, and then the ammonia and the HCl can react again to give ammonium chloride, and then the ammonium chloride can break up again, and so on. So this is a reversible reaction. Now, the reaction keeps going forward and backward until what? Until we reach a state of dynamic equilibrium. For example, if we have this equation or this reaction, we have nitrogen dioxide gas is brown. Now, if it reacts so that it dimerizes, two of them react together, it forms N2O4, which is a colorless gas. And then the colorless gas will again change into a brown gas, and then the brown gas will become colorless. Now, this will continue going forward and backward until what? Until we reach equilibrium. Now, what is equilibrium? Equilibrium means the rate of forward reaction equals the rate of backward reaction. So the concentrations of reactants and products remain constant. So this reaction keeps going from brown to colorless, colorless to brown, until at some point it becomes one state in which it is somewhere in between the brown and the colorless. So it appears as if there is nothing happening, but actually what is happening is the forward reaction is happening at the same rate as the backward reaction, so that the concentrations of the NO2 and the N2O4 remain constant, so they don't change. This is called dynamic equilibrium. Now, according to Le Chatelier's principle, if a system is in dynamic equilibrium, then it is subjected to a change. The position of the equilibrium shifts in the direction which reduces the change. So I want to remain at the state of equilibrium. But if we change anything, if we decrease something, then the reaction will try to increase it back. If we increase something, then the reaction will try to decrease it back to return back to the state of equilibrium. What does that mean? For example, if I have this process, do you remember the name of this process? We said this is the Haber process, and this is nitrogen plus hydrogen to give ammonia. Now, if we're trying to make ammonia, then we want the reaction to go forward. We don't want it to go backward. So we try to adjust the conditions in order to force this reaction to go more forward, to give more ammonia. So what can I do to the reaction to give more ammonia, for example? I can change temperature or pressure. If we're talking about gases, since this reaction involves only gases, then we can change pressure, and we can either add more reactants or add products, or remove reactants or remove products. This is how you change the point of equilibrium. Point of equilibrium means, is it going to go forward or is it going to go backward? So one of the factors that we can change is pressure. And we said pressure, we can use it only in case of gases. And you have to know that increasing pressure on a reversible reaction forces the reaction to go to the side that has less number of moles. What do we mean by less number of moles? Remember that we said the balancing of an equation is actually the ratio of moles. So in this reaction, if we go forward, we form 2 moles of ammonia. If we go back, we form 1 mole of nitrogen and 3 moles of hydrogen. And we're saying if we increase the pressure on this reaction, then increasing the pressure means the particles come closer to each other. This becomes more crowded, so it wants to go to the side that will make it less crowded. So it goes to the side that has less number of moles. So in this case, will it go forward or backward? Well, in this case, if I increase pressure, then the equilibrium will shift to the right. That means it will go forward in order to give less number of moles. So if we say what is the effect of increasing pressure on this reaction, increasing pressure will cause the point of equilibrium to move to the right, or it forces the forward reaction, or it favors the forward reaction. If we're talking about what is the effect on the yield of ammonia, you should know that if it goes forward, then it will give more ammonia, and that means the yield will increase. So for this reaction, I should be using a high pressure. But actually, we cannot go too high. So if we go too high, remember that to put a pressure on a reaction involving gases, we need special apparatus. So using very high pressure would be too expensive, and therefore this reaction is carried out at a pressure of 200 atm. So the 200 atm is high enough in order to give more yield of ammonia, but any higher pressure would be more expensive, and any lower pressure will cause the reaction to go back, and that means less ammonia. Are we following the explanations of all of this? So let's take some questions. For example, this question says the cracking of alkanes is carried out at high temperature. When the pressure is increased, the reaction shifts to where? So in this equation, if I increase the pressure, remember we said increasing the pressure causes the reaction to go to which side? To the side that has less number of moles. So in this equation, if I increase pressure, going forward gives total 3 moles of products. Going back, it gives 1 mole of product. So in this case, if I increase pressure, then it goes to the side with less number of moles, and that means it goes to the left in order. Okay, this is another question. The reversible reaction between hydrogen chloride and oxygen produces water vapor and chlorine, and that means all of them are gases. Explain what effect an increase in the total pressure has on the yield of chlorine. So if we increase the pressure in this reaction, will it go forward or backward? You should remember, increasing the pressure causes the equilibrium to go to the side that is the one with less number of moles. So increasing pressure goes to the side with less number of moles. Which side here has less number of moles? If we go forward, it forms 2 water and 2 chlorine. So that's a total of 4 moles. If we go backward, it forms 4 HCl and 1 O2. That's a total of 5. And that means if we increase the pressure in this reaction, the point of equilibrium shifts to the side with less number of moles, so it goes forward, or it shifts to the right. And that means it will form more chlorine or more yield of chlorine. What about this reaction? State the effect of increasing pressure on this reaction. Again, increasing pressure, we said it should go to the side with less number of moles. So, in this equation, if it goes forward, it forms 2 HI. If it goes back, it forms 1 H2 and 1 I2, and that means a total of 2 again. So that means in this equation, if I go forward, it forms 2 moles. If it goes backward, it forms also 2 moles. So in this reaction, if the number of moles on both sides are the same, then there is no effect of increasing the pressure. The pressure, when we increase it, it should go to the side with less number of moles. If both sides are equal, then increasing pressure will have no effect on the point of equilibrium. The other factor we can change is temperature. So remember, when we're talking about pressure, we were looking at which side gives less moles. But when we're looking at temperature, we're going to look at which side is exothermic and which side is endothermic. Remember the delta H that we have here at the end of the equation. Delta H is the heat change or the enthalpy change. If the delta H is negative, that means the forward reaction is exothermic. So if it gives me that the delta H is negative, then that means the forward is exothermic. That means the backward is endothermic. Now, if we increase the temperature, the reaction will go to which side? Remember, increasing the temperature forces the reaction to go to the side that is endothermic, so that it uses up the excess heat. We want the amount of heat in the reaction to be the same. We don't want it to change. So increasing the temperature causes the reaction to go to the side that is endo. So if here the forward is exo, then in this case, increasing the temperature shifts the equilibrium to the left, or it causes the reaction to go backward. Of course, if the reaction goes backward, that means the ammonia is breaking up, and that means the yield of ammonia is less, or we will get less ammonia. That means for a reaction like this, I should be using a low temperature. Low, if we say increasing goes endo, that means decreasing goes exo. So in order to force it to go forward, I should decrease the temperature. We said increasing the temperature goes backward. That means in order to go forward, I need to decrease the temperature. But if I decrease it too much, this will have an effect on something else. This will have an effect on the rate. Remember, for any reaction, if the temperature is low, the rate is low. So we don't want the rate to be too low. So for this reaction, we do the reaction at 450 degrees Celsius. Now, if it's asking why not more than 450, because more than 450 will cause the reaction to go back and I get less ammonia. But why not less than 450, since less than 450 will cause the reaction to go forward, but then the reaction will be too slow. So what we do is we do it at 450, and whatever reactants remain, we recycle and reuse it in order to have as high a yield of ammonia as possible. Are we following? So, for example, in this reaction, follow with me. We want to change the temperature, for example, to go forward. Now, this reaction says that the delta H is plus. That means the forward is exo or endo. If delta H is positive, that means the forward is endothermic, and that means for this reaction, increasing the temperature will cause it to go forward, because we said increasing the temperature, it goes endo. So for this reaction, if I want it to go forward, I increase the temperature. This will cause the point of equilibrium to shift to the right, or the reaction goes forward since it is endothermic, to use up the excess heat. Again, this was the contact process, and from this information it says that the forward is exo or endo. Delta H is negative, that means the forward is exothermic. That means as it goes forward, it heats itself up. Now, the question says, explain the effect of an increase in temperature on the yield. So if we increase the temperature, remember, increasing the temperature, reaction goes endo. So if for this reaction the forward is exo, that means if I increase the temperature, it will go backward, because that is the one that is endothermic. So the forward reaction is exothermic. How did I know? Because the delta H is negative. So increasing the temperature, I should know, goes to the side that is endo. So if the forward is exo, that means the backward is endo. So increasing the temperature shifts the equilibrium to the left. But that means that the SO3 is breaking up to give SO2 plus O2, and that means the yield of sulfur trioxide would decrease. Again, let's take a look at this. This one says the delta H is minus 114. That means the forward reaction is exothermic. Now, what is the effect of increase in temperature on the yield of chlorine? So if I increase temperature, will it go forward or backward? We said increasing temperature goes to the side that is endo. If the forward is exo, that means the backward is endo, and that means increasing the temperature causes the point of equilibrium to shift to the left or to go back, since the forward reaction is exothermic. And if it goes backward, what happens to the yield of chlorine? Then we will get less chlorine, or we say the yield of chlorine decreases. Another question, nitrogen reacts with hydrogen to form ammonia. The highest equilibrium yield for this reaction is produced at what? For this reaction to give me more ammonia, should I use high temperature or low temperature? We said the forward delta H is negative. That means the forward is exo. If I wanted to go exo, I should lower the temperature, because we said increasing temperature goes endo. يبقى decreasing the temperature goes exo. So for this reaction, I need low temperature. So C or D. And remember, we said, do we need high pressure or low pressure? We said when we're talking about temperature, we look at delta H. But when we're talking about pressure, we look at which side gives less moles. So we said, I want to go forward. Forward is less moles. We get less moles with higher pressure. So in order to go forward, I need a lower temperature and a higher pressure. This reaction is called the Oswald process to form nitric acid. Which of the following would decrease the yield of nitrogen monoxide. So NO, I want less NO. Less NO means I want it to go back. In order to go back, remember, looking at the equation, the delta H is negative. So if I want it to go back, then the backward is endothermic. So I should increase temperature. So I want increasing the temperature. What about the pressure? If I want it to go backward, backward forms 4 plus 5, that's 9. Forward will form 4 plus 6, that's 10. So if I want to go backward, then we're forming less number of moles, so I should increase the pressure. And that means if I want less yield of NO, I should increase the pressure to go to the side with less number of moles, and I should increase the temperature because the backward is endothermic, and increasing the temperature goes. Okay, this is another question. We have ethene plus water to give ethanol, and it tells me that the delta H is negative, and that means the forward reaction is exothermic. The manufacture of ethanol is carried out at 230 degrees Celsius, 70-80 M, and the overall conversion into ethanol is 95%. Comment on these conditions in relation to their effect on the equilibrium and the overall yield of ethanol. So, we're using 230 degrees Celsius. Should we be using higher temperature? Of course, any higher temperature will cause the reaction to go back. So using 230, this is a temperature that will give more yield of ammonia. What about the pressure? 70-80 M, we use high pressure because this favors the forward reaction to form less number of moles, so there is more yield of ethanol. The high temperature would shift the equilibrium to the left, since the forward reaction is exothermic. So a lower yield of ethanol, because I'm using 230, for example, not anything less. But if I use any less, that would affect the rate. So we're using 230, or we're using high temperature. It will shift the reaction backwards, so that affects the yield of ethanol, but I cannot use a lower temperature because the rate would be too slow. So the high temperature increases the rate, and the reactants can be recycled to give a higher yield. Okay, what other factors can we change? So far we've been changing temperature and pressure. We can also change the concentration or the amounts of reactants or products. And this is by either adding more reactants or removing products. So for this reaction, if I add reactants or remove the products, it will always favor forward reaction. So in this case, I add more nitrogen, more hydrogen. The reaction will go forward to use up the nitrogen and hydrogen, and this gives a higher yield of ammonia. What if I add ammonia to the reaction? If we add products, then the reaction goes back. This favors the backward reaction because the ammonia will be too much and it would want to use it up to return to the original concentration. So adding products causes the reaction to move backward, and that means the ammonia breaks up to give more nitrogen and hydrogen. So for this reaction, for the Haber process, if I want to go forward, the ammonia is cooled and liquefied to remove it from the mixture as it is formed. So if I try every time it forms ammonia, I cool it and remove the ammonia, this will form a liquid and it will be removed from the reaction. Then the reaction will try to make more ammonia. This forces the reaction to go forward, and this gives more yield of ammonia. So, for example, if I have this question, it says I have This is dichromate ion, Cr2O7, 2-. This is orange in color. Now, when you react it with water, this gives the chromate ion, CrO4, 2-, and that is yellow. So, the question says, if we add a small amount of sodium hydroxide, what would happen to the equilibrium mixture? The reaction doesn't have sodium hydroxide in it. So we're not adding reactants or we're adding products, but the sodium hydroxide is a base. Now this equation forms H+, so it forms acid. So as it goes forward, it forms acid. Now if I add sodium hydroxide, the sodium hydroxide will use up this acid. The sodium hydroxide will react with the acid. So it's as if I am removing the H+ from the reaction, and we said if we remove products, then the reaction will try to go forward to form more H+, so that we return back to the original concentration of H+ ion. So in this reaction, if I add sodium hydroxide, it will remove the H+. So the reaction will try to go more forward, so the orange will turn to yellow, or this causes the equilibrium position to turn to the right. Effect of catalyst. Now, we should know that a catalyst is a substance that speeds up any reaction. For a reversible reaction, the catalyst speeds up both forward and backward reaction. So, nitrogen and hydrogen to form ammonia, and ammonia breaking up to form nitrogen and hydrogen, both of these reactions will be faster. So actually a catalyst does not force this reaction to go more forward or more backward, so it has no effect on the point of equilibrium. So remember, adding a catalyst would only make the reaction faster. Remember, the catalyst makes the reaction faster because it lowers the energy of activation. So the temperature does not have to be too high, and this saves energy, and that is why we use a catalyst. But we don't use it in order to form more ammonia or less ammonia. So, for example, this reaction says HCl plus oxygen to give H2O plus chlorine. The forward is exothermic. Now, explain what effect the use of a catalyst has on the yield of chlorine. How will it increase the amount of chlorine, decrease the amount of chlorine? Remember, we said a catalyst speeds up both forward and backward reactions, so there is no effect on the point of equilibrium, so the concentration of chlorine that is obtained will remain the same. We're not forming more chlorine and we're not breaking up any chlorine. We're speeding up both forward and backward reaction. So, for example, the Haber process. What are the suitable conditions to make as much ammonia as possible? We said the forward is exo. So, we need to use a temperature that is not too high. So, we use 450 and not, for example, 1000. Why? Because increasing the temperature will cause the reaction to go backward. We're using 200 atm. That means we're using a high pressure. Why are we using a high pressure? Because the high pressure will cause the reaction to go forward to give less number of moles. But any higher pressure would be too expensive. Now, we're using a catalyst for this reaction. The catalyst is iron or finely divided iron as a catalyst. And we said, since it's a reversible reaction, some of the ammonia will break up to form nitrogen and hydrogen, but then we can recycle the nitrogen and hydrogen again over the catalyst, so we can get as much ammonia as possible. In addition to the fact that we said as the ammonia is formed, we cool and liquefy it, so it's removed from the reaction, and that causes the reaction to go more forward to form more ammonia to replace what has been lost. Contact process is the reaction of SO2 plus O2 to give SO3. Now, what are the conditions of this reaction? We do it again at 450 degrees Celsius because the forward reaction is exo, so any higher temperature would cause it to go backward, and any lower temperature would make it slower. We use it at 2 atm. Of course, looking at the equation, using a high pressure forces the reaction to go forward to give less number of moles. Why don't we use 2? Instead of 2, we use 4 or 10 or 20 or 200, because a higher pressure would be too expensive. Catalyst in this equation is vanadium pentoxide, or V2O5 is used as a catalyst. So that's the end of this about reversible reactions. I hope this made the topic a bit clearer. Thank you for listening.